progress, really. So it's been recording this entire time. But anyway, so let's go ahead and pick up where we left off. That look about right? Yeah. The open stacks? Oh, okay. So let me just, so the question is access to OpenStax. Let me just kind of do a little bit of a redirect here. And what I will do is I will, I guess, do it here on my iPad Pro. So it should be under content. It should be available to you. Okay, let me see then what's going on here. Story of CCD, secure but not functional. Okay, so under content, let me see here. So it wasn't coming up with any of this stuff? This would be the, yeah. So the OpenStax, this is basically like a link to OpenStax, and it takes you to like the book material. They've got it kind of divvied up by topic is what they do. So I think with OpenStax, when they kind of take you into your system, they might have you like create an account to log in there, but it's all open course. It's all open. So you just creating, it doesn't like cost you anything to create the account, but sometimes they'll create the account a lot of times because people like me, like in the middle of the semester, will decide like, oh, I will actually want to do something that requires an account on OpenStax, like an assignment or something like that, like if you're administering an assignment. And then if you've already got the account, then you already have that access. So that's an easier toggle point. They also want to keep track of who's using their stuff, right? That's kind of how they build their business, is if they have a head count of who's using it all, then that's how they kind of grow things. They win investors, they broaden their ability. That make sense? Did that fix the problem? Because it should be like just a topic. You just click on it and just takes you directly to the actual link itself, and that's the textbook. So that's kind of that OpenStax. It's free. It's not like, you know, your normal textbook. It's not bad, but you know, it's a little bit different. But that's, you know, it's free. that's the right price for any of that stuff. That makes sense. That solve your problem, Betsy? A little bit. Yeah, try it out. That's the way they are, all of them. There's like an intro, there's like a chapter outline usually associated with all of the chapters, and then instead of having like a chapter, like chapter 2, whatever, it's like they break it up by topic. Yeah, it's kind of a little bit different, but not a bad kind of different, just different. Okay, so we left off talking about elements. Yes. So let's keep talking about them, actually. So when we have elements, where we said we have all these different elements that we have on the periodic table, And the question is, we're not really interested in all of them, right? So in chemistry and physics, we're interested in all of them. We want to sort of take a look at all 90 some odd elements and sort of play around with them to varying degrees. But in biology, we're only interested in what actually makes up a biological organism. And the question is, what exactly is that, right? So as it turns out, of the 90 naturally occurring, there's really not that many elements that you're going to find in a biological organism. So for instance, if you were to take us or any living organism, for instance, break it all down at the elemental level or the atomic level, what you would end up getting is basically these 12 elements. That's pretty much it. All the 92, you only have maybe roughly around 10-ish or so % of them represented in biology. And not only that, but of these, they're not all equally proportioned. By overwhelming lion's share of them, I mean, we're talking north of 96%, is going to be composed of 4 atoms: carbon, hydrogen, oxygen, and nitrogen, CHON, basically. And that's like the lion's share of it, right? Now, oftentimes, especially, and I kind of like to use this because when we take a look at living organisms, we think of like all these crazy things going on in our body. We talk about nutrition, all these sorts of things, right? And we have all these multivitamins we're taking. We're looking at things like magnesium and calcium and all these sorts of things, right? But it kind of sets some students back every now and then when they take a look at this and they realize, wait a minute, that's like the overwhelming majority of what my body's made of is carbon, hydrogen, oxygen, nitrogen, those 4. Now, what about the others, right? So if sodium and magnesium and calcium are so important, then why aren't they more, right? Well, one of the things I always want to point out, which is something that oftentimes students will fall into, is what I call the Texas problem, right? Bigger the better, right? Everything in Texas is big. Texas itself is kind of big, right? Right. So that kind of Texas mentality. Well, that actually doesn't work in biology. In biology, it's kind of not so much like big as much as it is specialized. So for instance, if you were to take a look at the remaining isotopes here, you could easily, and sometimes you do, and erroneously, I would say, make the assumption that because these guys are in low proportion in an organism, that they're also less important. Nothing could be further from the truth. As a matter of fact, most of these ions here, if you didn't have them, would essentially kill you. Here's a good example: sodium, right? We talk a lot about sodium in life, don't we? You're either having too much of it or not enough of it. You've got it's a blood pressure issue. So we have a lot of discussions around sodium, right? But sodium is actually a very, very small fraction of your overall atomic makeup. However, if you didn't have sodium, because we always like demonize sodium, and usually when our discussions of sodium are bad, like, oh, that's too much salt, don't eat that much salt. Well, if you didn't have any sodium, you'd be dead. Why? Because the entire backbone of how your nervous system sends a nervous impulse is based on sodium. So if you didn't have any sodium, you wouldn't literally have no nervous system. That's a pretty big deal. Or calcium, for instance, right? Calcium is also a tiny fraction of your body. But if you didn't have any calcium, you would also be dead. Why? Calcium does a lot of things in your body, but one of the main things it does is it's a major ion involved in muscle contraction. So if you don't have calcium, you're not going to be able to contract your muscles. Of course, now you're thinking, well, that's fine. So I won't be able to move. I could just be like a little banana slug or something like that. I'm cool with that. Well, no, you're not. Why? Because not only will you not be able to contract your skeletal muscles, you won't be able to contract the most important muscle in your body, which is your heart, which also is a muscle and also requires calcium. So if you didn't have calcium in your diet or in your system, you wouldn't have a fundamental capacity to actually pump your heart, which means you would have no heartbeat, which means you'd be dead, right? So these ideas that there's little bits of these ions in your body is something we refer to as trace elements. That means it's like if you think in terms of like culinary, if you're culinarily trained, you see spice usually in a different way than just the average bear, right? The average bear will take a look at garlic, for instance, and just like, if you love a garlic, just like, let's give me the whole garlic, I'll eat it whole, right?
But if you're culinarily trained, you realize that garlic is a spice that has a very strong flavor to it. And not only that, but you're trained to get balance of flavors and to get different flavor spectrums, for which, if that's the case, adding a spice that's overwhelming can easily overwhelm the dish and completely destroy what you're going for. So in that case, garlic, for instance, would be considered a trace element. Is it an important piece of the dish? Absolutely. It kind of pulls everything together. But if you add too much of it, you've killed your dish. Or too little of it, and you've killed your dish. Is the dish mostly garlic? No. But is the garlic the deal breaker? Absolutely. Okay. A lot of times we feel the same way about salt. How many of you guys like eating unsalted food? Come on, you salt lovers. It's one of our 3 major instinctual cravings. I know you love salt. Why? Because you're all mammals, and you can't lie about it. You love salt almost as much as you love sugar.
What's the concept between taking cilantro?
Wait, what are they doing?
So some people don't like cilantro because it tastes like soap to them.
Yep.
Some people like it.
You know what? That's a good question. I'm glad you asked it. But that's a question for a later chapter. There is an answer to that, and we oftentimes do cover it in the genetics chapter. So hold that one. So I'll ask you when we get to chapter 12. So you remember your question you're supposed to be remembering all semester long? Right. But no, there is an answer to that one, but it's a genetic answer. And that's why we usually cover it once we get into genetics, especially like in the genetics lab. But you're right. Just if you're wondering, I'm a soap taster. I can't stand cilantro. I'm okay with it in small amounts because I can tolerate the perfumey taste in low levels, but too much of it, and it's just give me a bar of soap. It's the same effect. You're pretty much ruining the dish for me. So that's why it's I always watch cooker. They're like, oh, it had a generous amount of cilantro. It's like, why? Because I'm out. Right? You just lost me. As soon as you did that, I'm gone. Okay. So yeah. And some of you guys are not soap tasters, and we'll see that in the genetics lab. So, okay, so now what we have is these elements, right? Of which the lion's share of them are carbon, hydrogen, oxygen, and nitrogen. Now the question is, remember, we already talked about octet rule, yes? We talked about the driving motivation of atoms, the fact that they are striving to get to that perfection state, right? That's what they're going for. So now that we kind of have their motivation, we kind of know who they are, at least in the biological list, where we have our list of atoms that we're going to be using. Now the question is, how do we go about putting these guys together, right? Because we already enlisted by the octet rule that these atoms are striving to achieve perfection by doing what? By forming bonds or associations with each other so that they can kind of partner together in order to cover each other's imperfections, if you will, right? So together we're perfect, apart we're tragic, right? So, and that's kind of the idea. So the question is then, let's take a look at these chemical bonds. Let's take a look at these atomic associations and how these different atoms can actually come together in order to form these associations, because it's the discussion of how they come together and then what they do together as a team that then will give us the biological function that we're looking for. Okay. So first thing I want to do is list out the different bonds, and what I want to do is I want to do it right about there, maybe. So I'm going to lay down a slide. We're going to take a look at
Take a look at chemical bonds. So the first one that we want to basically take a look at is what's called the ionic bond. We kind of already looked at this one a little bit, right? So the ionic bond essentially is whenever two atoms are essentially gaining or losing electrons. It's a little bit different than the redox reaction in the sense that what happens is these specific bonds, like sodium and oxygen, basically will kind of do the sort of an electron transfer. That's basically what they'll do, right? So we already know about sodium, right? We know that sodium wants to get rid of its electron. So when it sees chlorine, it'll basically give chlorine that electron, and they're okay with that, right? So what that basically means then is sodium gets to fall back on its lower shell, yes, which is full, but it's also lost an electron, hasn't it? So sodium in its happy place exists as a sodium ion with a +1 charge, right? Chlorine, however, has gained the electron. So it basically in its happy place will exist as a chloride ion. However, this is them in perfection, right? They've managed to achieve perfection, but notice that they're only going to achieve this within the context of the relationship that they've agreed upon between each other. And that agreement centers around how to manage the possession of this electron, okay? And so we're going to talk a little bit more about that, but just to kind of fill this out, when you kind of create these ionic compounds, that is these charge-bearing compounds, typically what will happen, like if you take a look at a salt crystal, because they're charged and that's their happy place, right, in the charged state, then typically what will happen is they'll stack in an orderly form so that the charges sort of sort themselves out. That is to say that the opposite charges will attract to each other. So for instance, here's a good example. Notice you have a big negative charge right here in the middle, but it surrounds itself by 4 positive charges. Same thing with the positive charge will be surrounded by 4 negative charges. So what that basically means is you're stacking these ions so that each positive is in contact with a negative. And that kind of creates this sort of very orderly kind of, in this case, a very cubical type of crystal. Okay, and that's a salt crystal. And we get that with ionic bonds. But one thing I want to do, and that's kind of the first bond that we have, but one thing that I want to do is sort of sketch out the idea of bonding with relationship to one particular physical trait that's associated with elements, because that'll help us to understand better this idea of covalent bonds, which is another type of chemical bond. So let me go to my list here and start writing some stuff down. So the first bond that we have is the ionic bond. This is basically a bond between two atoms with very different electronegativities. Where there is a transfer of electrons. And that's the key piece here. Okay. Let me define a term here that I use in the definition. Nothing like a definition that requires more definition. So that's where I want to go next, because what I want to do is I want to skip forward a little bit, unpack this particular idea, and then come back and sort of start filling in our knowledge of the bonds with respect to this governing principle. And that governing principle is something called electronegativity. Electronegativity is a chemical property. It's an intrinsic, innate chemical property of all elements. And there's several of these. Actually, if you're in chemistry, there's a section in chemistry where you kind of go through it, and you go through this region, this period of chemistry we call periodicity, right? So there's different traits or chemical, physical properties of elements that show periodicity. What that means is that the traits themselves are predictable based on how the periodic table is oriented, right? So the periodic table, remember, is organized by atomic number, right? 1 proton here, 2 protons, 3 protons. You just kind of number it, and you just kind of, that's the way you ordered it. As it turns out, that order is also very predictive of a lot of chemical behavior of those atoms.
And so when you take a look, that's what we mean by periodicity. It means we can use their arrangement in atomic order on the periodic table to predict what their chemical behavior is. And actually, that's the cool thing about chemistry, is there's a lot of chemical behavior that you don't even need to do any wet chemistry on these things at all, because the periodic table is such a strong tool, such a valuable tool, that you can predict the chemical behavior just by the periodic table. And you can just overlay one physical property after another, after another, after another on the periodic table, and everything just fits together perfectly on the periodic table. And all we did was order it by atomic number. So, usually we were expecting, we have to reorder this, right? So we're going to order it by atomic number. Now we're going to reorder it in terms of electronegativity. And now we're going to reorder it in terms of, something else. But it didn't work out that way. It worked out that there was no reordering necessary. Everything just laid out perfectly on the periodic table. It's actually quite elegant. Once you get to that point, you realize this is like an amazing document. We totally lucked into this. I don't think Mendeleev knew that that's how it was going to go down when he first started putting all that all together. But anyway, what exactly is electronegativity? Like I said, it's something that all atoms have. And essentially, for lack of a better definition, though the better definition is, but basically this defines the affinity that an element has for electrons. In a lot of ways, I like to think of this as electron suckiness. Right, that's my technical term. That basically means that different atoms have a sucking effect on electron density. Think about this. When atoms are in a bond with each other, there is their own electron cloud in the atom, but now they're having to negotiate their electron cloud with respect to their partner's electron cloud. So a molecule's electron cloud is sort of like an amalgam or a hybrid of the two clouds of the two atoms, kind of sort it all out and sort of come to a truce. Well, the thing is, if an atom has a strong sucking effect on the electrons, it's going to basically pull the electron cloud over toward itself, kind of like stealing the blankets from your partner, right? So you're going to get all the blankets, your partner's going to be out in the cold. That's electronegativity. So we said it was periodic, right? So you can predict this in the periodic table. Well, the question is, what exactly is that periodicity? How do you determine it? Well, it's very easy. If you draw a periodic table, so there's my periodic table, electronegativity increases going up and over. So if we have two atoms in bond with each other, then depending on what their electronegativities are, one may have a stronger sucking effect on the electron cloud than the other. That has consequences.
That's in line with the transfer, correct?
Yes, everything about our bonds can be described with respect to electronegativity, which is the reason why I cover it first, and then we're going to double back around and then start to fill in how our bonds work. So electronegativity basically will, not that one, ignore that one, will form our two covalent bonds. So what kind of covalent bonds do we have?
Is that right?
Yep, no, you're right.
Non-polar and polar?
So a covalent bond itself is basically a bond between two atoms where the electrons are shared, not transferred, right? That's to be compared with transfer. Now there's two different versions of it, right? So as Jared said, there's non-polar and then there's polar. So polar is basically where the electrons are equally shared. And a polar bond is where the electrons are unequally shared. So let's take a look at this. So this right here is a list of nonpolar covalent bonds. So it's helpful to illustrate what a nonpolar covalent bond looks like. It's also helpful to kind of show you how, like, the nature between single, double, and triple bonds. Okay, so let's take a look at hydrogen. Hydrogen is the simplest of them all. So if you take a look at hydrogen, hydrogen has one proton, one electron. So it's got basically a valence of 1, right? And so how many electrons do you need to fill your shell? 1 in this case, right? Because you're still on that first level. So you just need another one. Well, guess what? You see another hydrogen hanging out over here. Guess what? If you guys share these electrons, you're going to form a bond. So a bond basically is a pair of shared electrons. So whenever we draw that line, that's a pair of shared electrons. And this is kind of what it looks like. So you can see they're sharing that. Now here's the thing. The difference between the electronegativity of this guy right here and the electronegativity of this guy is one greater, less than, or equal to the other. They're the same thing, right? So they have the exact same electronegativity. Therefore, they're nonpolar. It's like a stalemate. So it's like they're equally sharing this electron. Now, if you take a look at oxygen, right? Oxygen has 6 valence electrons, 1, 2, 3, 4, 5, and then we'll do 6 there. And then this one here, 1, 2, 3, 4, 5, and then 6, something like that. Now, oxygen sees another oxygen and says, hey, guess what? I need another electron. You have an electron. Why don't we go ahead and share this one? We'll form a bond. Okay, that's cool, right? But then guess what? They say like, well, wait a minute. I got another one. You? So yeah, I have another one too. Well, why don't we make another bond? There you go. We'll make a double bond. So that basically gets to your double covalent bond. And this is actually how oxygen exists in nature, as a double bonded structure. Now, nitrogen has the capacity to form 3 bonds. So you can see a pair here, and a pair there. That's about the only one, though, that can form 3 bonds. Okay. They can also form 3 bonds with other things as well. So you can form, say, for instance, something like this. Not sure what that is, but I forget. That's an organic chemistry thing. It's like an amine group or something like that, or a amine group. It's a weird molecule, but I used to know it in organic chemistry, but you don't ever see it. So the triple bond is very rare, like very rare. Mostly what you see are single and double, because triple bonds are just tough to deal with. Even when you're dealing with nitrogen, you don't see a lot of triply bonded nitrogens typically. Generally only elemental nitrogen. So this basically would be what we see in our atmosphere. So our atmosphere is mostly nitrogen. It's mostly elemental nitrogen. It's triply bonded nitrogen. So this is an example of a nonpolar. Notice in all cases, the electronegativities of each partner are equal. Yes. So when we kind of go back here, then nonpolar covalent bond is typified by the electronegativity of atom A being equal to the electronegativity of atom B. You have to equally share that because your electronegativities are not different. Now then a polar is going to be a situation where the electronegativity of A is greater than the electronegativity of B to varying degrees. Right. And then, of course, in an ionic bond, you could say that the electronegativity of A is much, much, much greater than the electronegativity of B. As a matter of fact, when you take a look at the ionic bond usually is involved in a metal with a non-metal. Now, what you see, notice, equal electronegativities gives you nonpolar. Different electronegativities gives you polar, but still covalent. Wildly different electronegativities get so far extreme that you cross from covalent to ionic. So you go to the ultimate transfer. Now, what I want to do, because, well, we brought it up and I kind of liked seeing it, is, where is that? There. Should probably keep this up because I'm always pestering Bella for her periodic table. Right, so here's your periodic table of the elements. So when we're saying that this is primarily between a metal and a non-metal for ionic bonds, then where are the metals? Well, they're kind of all over the place, right? So we have over here in groups 1 and 2, we've got our alkaline earth metals, right? So these are metals. Then in here, we've got our transition metals. We tend not to do a whole lot with those in biology. You do a lot of work with those in chemistry. And then notice right here, this is where the zigzag line goes in. This is going to be sort of those pseudo metals right here. And these are all hardcore non-metals right here. So when we say that an ionic bond happens between a metal and a non-metal, oftentimes in biology purposes, most of what we're talking about usually are something way over here coming together with something way over here. For instance, sodium, which is over here, forming a relationship with chlorine, okay, which would be an ionic bond. Now, notice, remember the periodicity of electronegativity. Electronegativity goes up and over, right? So on the periodic table, who has the highest electronegativity? Hydrogens. So noble gases don't count because they're kind of like, they're perfect already, right? So they're like, screw you all, I'm out, right? So who would be left? Highest electronegativity would be the furthest up and over? Fluorine, right? Who has the lowest electronegativity? Helium. Yeah, that one, francium, right? Because you're all the way to the left and down, francium, right? So what that means is when you have molecules that have these guys with these guys, you have a strong disparity of polarization between the electronegativities, right? What does that mean? What that means is in a bond, chlorine has a stronger sucking effect on the electron than does sodium. So when these two are partnered up, that electron is going to be spending more time with chlorine. That make sense? Yeah. Not so much weight, but atomic size is also periodic. And that actually goes the opposite direction. So like francium is enormous and fluorine is pretty tiny. So it's kind of the opposite direction. But it doesn't really have an effect on necessarily electronegativity per se. That's the curious thing about these is they kind of seem to be independently periodic, like predictable in their pattern. And that's what's the cool thing about it. So then when you're talking then about covalent bonds, generally speaking, you're talking usually about non-metals with non-metals, right? So here's a good example, carbon dioxide, CO2, non-metal with a non-metal, right? So that would be an example of a covalent bond. The carbon-oxygen bond would be a covalent bond. Now, would it be a polar covalent or a non-polar covalent? Is it? So you're saying these guys have the same electronegativity, carbon and oxygen? No. Are they in the same spot? Who has the greater electronegativity? Oxygen, right? Now, is it strongly polar? No. But the bond is polar, right? And that's kind of the fun thing about polarity of the bond is you have the one extreme, the ionic bonds, right? Where there's a vast difference between the two. And those are easy, right? Those are dramatically polar. But then when you get to the covalent bonds, you have all these shades of polarity. You can either be very strongly polar or you can be very slightly polar. And different mixtures of that will give you different sort of sharing parameters of the electron cloud. This is the reason why every single time two atoms come together, it's a new relationship because it's not all the same. So for instance, the carbon-oxygen bond is not as polar as say the carbon-hydrogen bond, right? Because carbon and hydrogen are further apart in electronegativity. Therefore, oxygen is going to have the lion's share of it. Okay. And so That's get back to this one. So that's how basically electronegativity sort of defines how these bondings actually work, and how they kind of go down. Now, there's another thing that I also want to sort of use as sort of like, and I gave you some examples, first of all, of ionic, right? So we took a look at salt. So we saw an example of ionic. We saw an example, a couple of examples actually of covalent, right? So hydrogen and oxygen and nitrogen. So that was our covalent example, but I haven't really given you an example of what a polar one looks like yet, right? And what I want to do is I want to draw for you this guy right here. What is that? Yeah, it's water. So oxygen is oxygen electronegativity greater than, equal to, or less than hydrogen's? Its sucking effect. Well, where's oxygen on the periodic table? And how does electronegativity work? So the higher electronegativity is higher up and to the right. So again, question, is oxygen's electronegativity greater, less than, or equal to hydrogen? By a lot, right? Because hydrogen is all the way to the left. Oxygen is not quite all the way to the right, almost, right? So it's in group 6. So it's got one group left. The only way you could be stronger is if it was chlorine instead, or fluorine. So oxygen is pretty strong, right? So that means oxygen has a strong sucking effect. So when you take a look at the oxygen hydrogen bond that water is made of, then you would expect oxygen to take the electron cloud and suck it toward itself, right? Now, what this looks like within the context of a molecule is like this. Remember, you have this electron cloud, right? But because oxygen is electronegative, it's going to suck the lion's share of the electron cloud toward itself. What that means is the electrons are going to be spending more time around oxygen than around hydrogen, making the oxygen side of the molecule look slightly negative. The hydrogen side of the molecule is going to look slightly positive. What this basically means is you created a molecule that has a polarity to it. It has a negative-ish looking end and a positive looking end. That's a polar molecule. However, in chemistry, we have a term for this that I want you to be aware of. Because this is the way water is structured, right? It's never not like this. It's always got this negative end and positive end. It's polar. That's what it is. Because that's always stable, we call this a permanent dipole. It's a fancy word. All that means is you got two poles, two ends, a positive end and a negative end. It's permanent, which means that I can just throw a water molecule at you. Doesn't matter. It's always going to have a negative end and a positive end because it's a permanent dipole, right? Now, there's a couple of things I want you to parse out because there's two different levels of discussion here, and I want to make sure I kind of make this clear, but it's important to sort of tease this out to set us up for the next topic. Did you need it here?
Here's look at it.
Oh, yeah, they're all in the back. You want to look at them? We're just going to your chance to get away. So there's two levels of polarity, right? So I mentioned the P word. So we're talking about polarity. And so when you take a look at polarity, there's two different ways you can look at it, right? There's polarity of the bond. That's the one we just talked about, right? That's number B, polar covalent bonds. But now we've just talked about the molecule, haven't we? That's a different level. We just went up a level, right? We just went from the polar covalent bond to the overall molecule, which is composed in this case of polar covalent bonds. So in this case, the bond is polar, right? This is a polar covalent bond, and the molecule is polar as well, right? However, the two are not always the same. Here's an example. Let me use carbon, right? What is the valence of carbon? How many valence electrons does it have? You guys are like, I have no idea. Okay, how about this? Do you have an idea now? So how many electrons does it have?
6.
Okay, so let's bore this out, right? How many go on the first shell?
2.
2, right? How many do you have left over? And then what do? You stick those on the second shell, right? So how many valence electrons do you have? 4, right? Because you have 4 on that outermost shell, because you only have 6 electrons. 2 on the first shell, 4 on the second shell. Okay, so we have 4 electrons. That means we can form 4 bonds, right? So basically you have carbon, 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 carbon. It's going to form an association with hydrogen. There's another one here with hydrogen, another one here with hydrogen, and another one here with hydrogen. Okay, there's that. So we'll just kind of draw the lines there. This, by the way, do you know what this is? This is methane, a fart fane for you fart joke lovers, right? This is basically methane. Now, here's the thing. Let's take a look at the bond first, okay? Carbon, hydrogen bond. Is this a polar bond? Take a look at it. Where's carbon? And where's hydrogen? Is this a polar bond? That is to say, are these electronegativities the same? So is it a polar bond? Right? And who's the winner? Yeah, that's the one where it's going to get sucked over, right? It's going to get sucked over to carbon. Is it as strong as an oxygen-hydrogen bond? No, because carbon doesn't have as great of an electronegativity. So we know that that bond is polar covalent, right? But the question is the molecule polar? Well, let's take a look at it. Remember, so we have electron cloud being sucked toward carbon, yes? But remember, in order to be a polar molecule, you have to have a dipole. That means you have to have a negative end and a positive end. So your charge distribution has to get lopsided. If it doesn't get lopsided, then you're not a polar molecule, right? So if you take a look at it, all the electron density is going to be going where? Toward carbon. Yes? And looks like nice symmetrical order, right? From all directions. Can you identify a positive end and a negative end here? So this is an example of a nonpolar molecule. Not because it has nonpolar covalent bonds necessarily, but because it doesn't have that lopsided charge distribution at the molecular level. And there's a reason why I want you to think that way, right? Because sometimes we'll be looking at this at the bond level. We'll be like, okay, is this a polar or non-polar or polar covalent bond? And then sometimes we'll be looking at the molecular level. Notice what we did is we went one level up in our hierarchy. Hello, chapter 1, right? From kind of small bond that is at atomic level up to molecular level. And now we're looking at it from a slightly different point of view. Christopher, is there a question?
Yeah.
If it's for the molecule, you mean?
Yeah.
Like if the electron cloud shifted over to the hydrogens? It wouldn't, because it would still be a dipole. But it never does that, because the oxygen ensures that it doesn't do that. Because it literally is greedy for the electrons, and it's like, no, these are mine, right? Now, the important thing, and a lot of times, this right here, a lot of times when students hit this, it kind of like, okay, wait a minute, this is my quagmire point, right? This is my quicksand moment in chapter 2, one of my first ones, maybe not the first one. It could be maybe just one in many quicksand moments that you've already had. But the way I like to think about this, especially when you're talking about this issue of electrons, is it's helped sometimes to think about the way these atoms are behaving and their relationships with each other. Very similar to like custody sharing of like a couple over a kid. Because that's anthropomorphic, so we tend to understand that a bit more. Sometimes that's our own reality, so that we get that one a little bit better. But literally, the atoms are doing the exact same thing, right? So let's start with the most extreme custody scenario. That's ionic bonding. So from a social point of view, this is sort of like the one-night stand, right? All right, this is the thing where, you know, it was just a fling and there was like nothing to it. And it's like, listen, I don't know you, you don't know me. This was just a moment in time, but now we've got this kid, right? And I always like to pick on the deadbeat dads because oftentimes they are the primary deadbeats, or the traditional deadbeats. And of course, you know, they're like, oh, well, that's nice that you kept the kid. That's your problem. I'm out. You know, I never had a kid, so I don't know you. I don't know the kid. I'm just going to go on and live my life and pretend like this never happened. Right. Now that is a custody agreement that's pretty stark, isn't it? Clearly, there is a very strong will for one parent to have the kid, right? And then the other parent has the complete opposite. It's like, you know, I'm washing my hands of this, I'm out, right? So who's the deadbeat dad in the case of sodium chloride? Yes, sodium, right? Sodium's like, listen, hey, we just had a one-night stand. It turned into an electron, and listen, I'm out. You know, I'm just going to go live my life as sodium ion, and I'm going to pretend like nothing exists. I'm just going to go and do my thing, right? And unfortunately, we probably know a lot of people like that. Unfortunately. But then who about the other one? The other one's like, you know, well, no, right? Who's the mom in this case? The chlorine, right? In that situation, it's like, well, you know what? I've kind of waited my whole life. I've always wanted kids. Granted, maybe this isn't the way I wanted it, but you know what? I've got a kid. I've wanted this all my life. So yeah, you know, I'm going to hang on to this kid. This one's mine. So you piece of trash, you can go live your life because you're just a total creep, and the planet would be better if you just pretty much spontaneously combusted. And that's how it goes down a lot of times, right? Yeah, so we know how that goes. We've seen this one. We've seen these train wrecks a little bit before. So that's obviously an extreme version. That's like a wholesale transfer, right? Now, what about the covalent ones? Well, the covalent ones is a situation where, you know, where you actually have a marriage maybe, or a partnership, and you actually have kids together. So at some point, I guess you did love each other, but then, you know, for reasons that are not relevant to the discussion, things just don't work out. The relationship doesn't work out. And then, of course, now you've got this thing, this electron to deal with, right? So you got this kid, and you have to come up with some sort of a custody agreement about it. And that's what oftentimes consumes a lot of divorce court, is custody issues. And of course, those can come out in lots of different ways, right? So let's take a look, first of all, at the polar version of a custody agreement. Now, oftentimes, you know, typically there will be a dominant parent, right? Sort of the main parent that does most of the custody work of the kid. And then the other parent has an agreement for visitation in varying amounts, right? So it can be as little as holidays and birthdays, or it could be every weekend. And it varies, right? It varies on the two individuals involved. And that's kind of, so that kind of shade, and there's a lot of permutations in between, right? So there's a lot of variations of this, and you have a lot of contact or very little contact. And so the thing is also true for polar covalent bonds, because you've got different levels of attraction to the electron. Depending on the two partners involved, you can have any number of variations of just how strongly these electrons are going to be attracted to each of the individual parents, depending on who's involved. Okay. And so you have all these different shades of sort of like this joint custody situation. Now, every now and then you run into it, which is usually rarer, a situation where maybe a couple splits up, maybe it's an amicable splitting, where the two of them, kind of come to an agreement. They're not necessarily at each other's throats, but they have this kid and they realize, you know what, we're actually better as friends than we are as spouses. And so the relationship's over, but we're both in agreement and we're both like right here, eye to eye, when it comes to this kid and the responsibilities of what it takes for the child. And so in this case, it's more of an equal partnership, right? Where both parents are very actively involved, and they're working together as a team. Now, obviously, that's a little rare to come by, because usually when things go south in a relationship, you usually start loading your guns and sharpening your knives. Start learning your anatomy so you know how to cut the jugular if the spouse tries to come around again. But in some cases, it's an amicable parting and they realize they're adults, or it's like, you know what, this kind of isn't working, but we have this kid. So we can all agree on what to do for the kid. And that's an equal partnership. That's like non-polar covalent, where the two atoms have as an equal strength over the electrons and they share responsibility back and forth to it. And that's kind of what it's like. So why did I go over parsing the difference between polarity and non-polarity of a bond versus polarity and non-polarity of a molecule? The reason is because this is the next slide. When we get into the next slide forward, it's a slight topical shift, although they don't really make it obvious. And unfortunately, the slides don't make it this obvious, and most textbooks don't make it obvious, but this is an unfortunate misnomer. What we're talking about now is something a little bit different than what we've been talking about. The hydrogen bond starts this discussion off, and it's not a bond. None of these next two things are. These things are better characterized as intermolecular forces of attraction. Notice what I said, intermolecular. We are on the molecule level now, not the atomic bonding level now. So we're not talking about two atoms coming together to satisfy each other's octet rule. That's not what we're talking about now. What we're talking about now is two molecules composed of those covalent and ionic bonds that are now interacting with each other. So for instance, if you're a dipole and you have a positive end and a negative end, what does that mean about your ability to interact with, say, other water molecules or other polar molecules, which also have a positive and negative end? Okay, so what are those molecular interactions between each other at the molecular level? And the hydrogen bond is probably the first and the most important of all of them. So this is a weak bond. Covalent bonds, ionic bonds are strong bonds. If you want to break those bonds, and you can, you're going to have to do some work on that. We're going to add some energy on that. Those atoms do not want to come apart, right? After all, they just formed this agreement. And within this agreement, they've achieved perfection, everything they've wanted in the universe. So if you're going to split that up, you're going to have to add a lot of energy in there, because those atoms do not want to get split up, right? Because as soon as you break that bond, you've thrown them back into imperfection, and now they're all in disarray. So these guys are a little bit different in the fact that they are weak bonds, and they're not even bonds at all. So what hydrogen bond is simply, and I'm going to put the triple dots here, the meaning of definition. An H bond is simply an electrostatic attraction between the positive of a hydrogen of one molecule and the negative of an oxygen, nitrogen, or fluorine of another molecule. Now, in biology, we don't have fluorine. This is actually more of a chemistry definition, because in chemistry, you're going to be working with oxygen, nitrogen, fluorine. But actually in biology, in organisms, there is no fluorine. So you don't have any fluorine in your body. You do have lots of oxygen and nitrogen though, right? Because those are two members of CHON, right? So most of our attractions are between hydrogens and oxygen nitrogens. And that's kind of what it looks like. So because of negativity, if you have an oxygen on some sort of a molecule, whatever that is, remember that's going to be slightly negative, yes, because of its electronegativity to be pulling electron density toward itself. When it sees the slightly positive of a hydrogen on another molecule, that's going to basically form an electrostatic attraction that is the hydrogen bond. So basically, it's the exact same set of physics as what happens when you were to take a balloon and rub it on your head. If you take a balloon and rub it on your head, what happens to it? Just let it go. What happens to it? Yeah, does the balloon fall off of you? It sticks there, right? Does it stay there forever? No, right? So that's a couple of things. First of all, right, what's happening with the balloon, and this is the exact same set of physics, is you're creating an electrostatic attraction situation there, right? So what's happening when you're rubbing your head with a balloon is electrons are rubbing off of your hair onto the balloon. So your hair is becoming electron deficient, looking slightly positive. The balloon is becoming electron rich, looking slightly negative. Positive and negative is an electrostatic attraction. So what happens when you let it go? The positiveness of the electrons built up on the balloon are attracted to the positive, the negativeness of the electrons of the balloon are attracted to the positiveness of your hair. And so you basically get the balloon to stick electrostatically. And that's the same exact set of physics for hydrogen bonds. You have a positive and a negative that basically electrostatically sticks together, just like the balloon sticks to your head. However, is the balloon actually physically part of your head now? So this is what we mean by weak, right? When we say it's a weak bond, we say that it's removable typically, right? A covalent bond, being a strong bond, would be like taking the balloon and actually making it physically part of your head, right? So like if you took it off, you would have to, there'd be surgery involved, it would hurt, right? Because you'd probably have to remove something that's attached to you, right? That would be like a covalent bond. It is now part of you. But these are weak. So that means that basically you can just take that balloon and pull it off, right? No harm, no foul. And so that gives it its sort of transitory, which basically is a reversible characteristic. Now, any one hydrogen bond is weak. A single bond, a single hydrogen bond that is very weak. But they can be very strong in numbers. The gecko effect. How many of you guys have had a gecko? Or you've seen it at the pet store? They're really cool, aren't they? You see them walking up the side of the terrarium. And if you look at their little feet, but common question is like, wait a minute, okay, so you're kind of big, right? I mean, so how are you able to actually walk up the side of the glass? I mean, it's not like, if you take a look at their feet, they've kind of got these little slotted folds on their feet. They're like lateral slots. So it's not like they're suction cups, like an octopus. So you can't do the, and stick it on there, right? So that's not the way you do it. So how does the gecko actually manage to keep from falling off? It does do that, but we're going to talk about that here in just a second. What a gecko has on it is basically a lot of hydrogen bonds on its feet. Any one hydrogen bond is weak, but all of them together across the entire foot gives them enough support so that he can actually hang on to the glass and support his weight. Now, here's the reason why you don't have suction cups. Think about it. If you had suction cups on there, how easy would it be for the gecko to walk around? It'd take a lot more effort, wouldn't it? Because you'd be like, okay, right? And it's like you'd have to, there'd be a lot more work involved there. Doesn't want to do that, does he? So what does he want? He wants to be able to put his foot on the glass and hang on. But then when it comes to take his next step, he wants to be able to take his foot off easily. So that's reversibility, right? So you want to be able to attach and detach, detach and detach. That basically, the reversibility idea is like I mean, that is a common pattern in biology, right? And now if you watch the gecko do it, and one of my other sections, they said it's kind of cool because when you watch it, he doesn't just like take his foot up, he kind of peels it off. Why? Because if you were to just take it straight off, you would have to overcome the overall force of all those hydrogen bonds. Remember, we said in numbers, they can be quite strong. So probably if you try to take this foot like this, you'd be like, oh, I'm stuck, right? So what do? You peel it off slowly. So if you just take this little bit right here, this little strip of hydrogen bonds, you can peel off because they're not quite as strong because there's not as many of them. And you can slowly kind of start to do that. So you can kind of peel your foot off. What you're doing is you're saying, I can't pull you all off because together you're stronger than I want. But I can pull these guys off because there's not as many. So I'll pull those guys off, and then these guys and these guys and these guys, and I'll kind of peel my foot off the glass. Now, that's an important idea for a couple of reasons. First of all, hydrogen bonds, actually more than anything we've gotten up to so far, is something that will actually be a major foundational component for biological applications in particular. Why? Because it basically single-handedly sets up all of the physical properties of water. And we're in a couple of slides, we're going to talk about those physical properties of water and how hydrogen bonds give those physical properties of water to us and what that means for us biologically, what that gives us in terms of biological capacity. Yep.
So, like, if you drop from a higher place and dive into the water, the higher you get, is that have to do with the amount of pressure that you would want to do?
So when you're diving into water, that's actually that's one of the properties of water. And so we'll talk about that. So you got a lot of good questions, but you're moving there, getting there sooner than I am. So keep that one. When we hit the first, actually, it's going to be in a couple of slides here. So what I want to do is I want to unpack that idea and sort of take a look at that concept with respect to some of the properties of water, those first ones we see. So once we understand those, then we'll take a look at an application of it. And that sounds like an application of one of those. So, okay, so that's basically hydrogen bonds. We see that obviously where? In polar molecules, right? So a hydrogen bond essentially is what holds polar molecules together. So that's great, right? But not all the world is polar, is it? What about non-polar stuff, right? When you pour oil out, do the oil molecules go flying around, flying apart from each other? No, the oil pours in a nice column, doesn't it? It doesn't just disintegrate or disappear on you. So the question is, if they don't have polarity to them, right, because they're non-polar, then how do they stick together, right? If you don't have this positive negative thing with non-polar molecules, then how is it that they're able to stick together the way polar molecules stick together? And the answer is another set of intermolecular forces of attraction, van der Waals forces, which is also a weak bond. It's actually even weaker than hydrogen bonds. And basically, in a van der Waals interaction, I want to kind of describe something here. Basically, when you take a look at van der Waals interaction, it's caused by, I'm going to lay a bunch of stuff on here, but I want to try to define them. By the ephemeral flickering clusters of charge in a nonpolar molecule creating what's called a temporary dipole. We call this a moment. Wow, a lot of baggage words in there, isn't there? So we got to unpack these bags. Okay, so I already kind of introduced the idea of dipole, right? So this is a molecule that has two poles. Now, what does it mean to be a temporary dipole? Well, just like we said with a polar molecule, it's a permanent dipole. It's always going to have a positive end and negative end. A temporary dipole is just that. It means it doesn't always have a positive and negative end. So let's take a look at this here for a second. So let's take a look at two nonpolar molecules like this. Now, both these molecules, remember, they have electrons whizzing around their cloud, and in both of them, remember, these electrons are just kind of like they're doing their thing. Now, as it turns out, as the electrons are whizzing through these clouds, from time to time, just by random probability, every now and then, the electrons will all kind of whiz around in such a way where they all converge in a single spot. Okay, but it's very brief. So they'll kind of all come together, and then they'll disband, and then they'll kind of all randomly come together again somewhere else, and then they'll disband, and they'll all randomly come together somewhere else, and then they'll disband. And it's just random luck just by how they sort of all come together. It's kind of like the lopsided washing machine effect, right? It's like every now and then, because they all just happen to converge in the same place, they'll kind of get all lopsided, and they'll create this little patch of negativity. So the point at which they're converging is this little cluster of charge. So the place where they're converging has a slightly negative because we're all negative, right? But the place that we've all vacated has a slightly, relatively speaking, positive look to it. So somewhere else where we're not has a slightly positive look to it. This is that cluster of charge. Now it's flickering, right? Because you don't last very long, because you just keep on moving. And so as soon as we converge, we disband, and we'll converge somewhere else, and disband and converge somewhere else. So it's like these little flickering clusters of negative charge that just sort of like, there it is, gone. There it is, gone. There it is, gone. Right? So the ephemeral part means it doesn't last very long. And it flickers off and on because the electrons are constantly moving and redistributing. However, as it turns out, this is enough to keep nonpolar molecules together. Why? Because in the molecule right next to me, I'm doing the same thing. Only my little cluster of charge is over here. My little positive flicker is over here. And for the moment in time that those two patches of charge are in place, I will feel a slight attraction between the positive-ish end of one molecule and the negative-ish end of the other before it disbands. But guess what? Another patch will reform somewhere else before I have a chance to sort of drift away. And then that will pull me back in. And then it'll disband, and I'll try to drift away. And then another patch will form, and then that'll kind of suck me back in. So nonpolar molecules basically will kind of suck toward each other when they form these little temporary dipoles. And then when they disband, they'll let go, and then they'll form it again, and they'll kind of pull together, and they'll let go, and they'll form together, and they'll let go. And that's just enough to keep these molecules glued to each other and associated with each other, which is the reason why when you pour oil out of a bottle, it pours in a column. Those oil molecules are all attached to each other by these forces of attraction. A lot of big words, but that's really important. Okay, so let's take a little bit of a look at chemical reactions. We got to sort of break down chemical reactions and talk a little bit about chemical reactions before we get to the next really big idea, which will finish us out in chapter 2, actually, and that's going to be taking a look at the properties of water. So in a chemical reaction, basically what you have is a process, remember, where atoms are forming associations with each other for the purpose of satisfying their octet rule, right? So they're getting themselves perfect. Don't ever lose sight of that. That's all a chemical reaction is. Generally speaking, when you take a look at a chemical reaction, you have reactants, which are the molecules that are coming together. You have a chemical process, so the reaction progress, and then you have the products, or essentially what you get out of the chemical reaction itself. Now, a couple of things that defines chemical reactions. One is called the law of conservation of mass. Anybody heard of that one? So it's a chemistry law. Basically what this says is that mass is neither created nor destroyed in a chemical reaction. So that means everything you see on the left has got to add up to everything you see on the right. Let's take a look at this for a second. Let's go with carbon. How many carbons do I have over here in the reactants? 6, right? And how many carbons over here in the products? Also 6, right? Okay. How about oxygens? So how many do I have in the reactants? So I've got 6 molecules of CO2, which has 2 oxygens per molecule. So I've got 6 times 2, which is 12, plus 6 more from my water. So how many do I have? 18. Now let's go over here. How many oxygens do I have here? So I have 12 here, right? Plus another 6. So I've got 18. How about my hydrogens? Let's take a look at those. How many hydrogens do I have in my reactants? 12, right? Because I've got 6 molecules of water with 2 hydrogens each. So that gives me 12 over here. And how many do I have in my products? 12. Did I lose anything? Did I gain anything? So then what's happening in a chemical reaction then? All that's happening in a chemical reaction is you're taking bonds that currently exist between 2 atoms, you're breaking those bonds, and you're just basically reassigning those connections to other atoms. So you break existing bonds and you create new bonds. That will give you new combinations of atoms that are more favorable biologically. For instance, if we take the bonds of water and CO2 and break them and rearrange those associations between the atoms, we create something much, much more beneficial for us, which is glucose. Right? And that's basically what a chemical reaction is doing. You're taking existing bonds, you're breaking them, and you're creating new bonds that give you more biological function and biological capacity. And that's what you're going for. So the other topic is, that's great. So we got these chemical reactions. So what sorts of things are going to influence these chemical reactions? That is to say, how can you change the rate of reaction? Well, number one, temperature. Temperature, basically, increasing temperature will increase your reaction rate. So in that case, we generally don't utilize this one in biology. We would actually have to increase the temperature like by a lot. It would actually kill us. But yeah, so when you're doing fever, that's usually you're trying to unfavor, if you will, or create more unfavorable conditions for the guys who are attacking. Okay, so and that's kind of what we're doing with the fever. So we can kind of tolerate a little bit of a temperature spike, but maybe the bacteria that's in us can't. And so the idea is if we make you a little weaker, then our immune system will have an easier time of dispatching them. That's kind of what the fever is about. Another way you can increase or decrease reaction rate is by either adding reactants that'll go forward in the reaction. That means you'll make more product, or if you add more products, that'll go backwards and make more reactants. So depending on which one of those you add, you can basically push your reaction either forward or in the backward direction. And the last one, probably the most important one we'll touch on a little bit later, is catalyst. So this basically is something that you add to a chemical reaction to do one thing in particular. First of all, every catalyst, regardless of where you are, has got to conform to 2 pieces of its definition. First of all, it has to be able to speed up a reaction. If it doesn't, it's not a catalyst. The second one, and it absolutely has to conform to this one too, is it can't be consumed. by the reaction or altered by the reaction. So a catalyst has to adhere to both of them. Are there things that speed up the reaction that are not catalysts? Sure, but they're consumed by the reaction, right? So that's not a catalyst. So you have to have both, right? So you can speed up the reaction and not be a catalyst. You cannot be consumed by the, but not do anything to the reaction. So you have to do both of these to be able to actually conform to the definition of the catalyst. Now, probably the one the most important thing in these two slides is this piece right here. The idea of reversibility. In chemistry, when we're looking at chemical reactions, we're oftentimes really focused on completion of reaction, right? And basically what that means is if we've got a chemical reaction where we have A plus B goes through some sort of chemical reaction to give us C plus D. In chemistry, we often are wanting to say, well, we want this to be a complete reaction. We want to get as much C and D as possible. And you do clever little things in chemistry like, you know, percent yield and how much do you get, right? So the idea is like to get your maximum percent yield, to get 100% yield for your theoretical yield to match your actual yield, your reaction has got to go to 100%, right? So you're oftentimes focused in that completed reaction. Generally speaking, it's not until Chem 2 that you start to get to things like equilibrium and stuff like that, where you start to talk about incomplete reactions. But in biology, we have absolutely no interest whatsoever, generally speaking, in completing reactions. We are always into reversible reactions. So we see this as like, listen, don't tell me something, you know, going forward if I can't go back, right? What does this do for us in biology? Well, what this basically means is that we have really two sets of molecules here. So say, for instance, a set of circumstances in the environment, perhaps, or whatever. Circumstance A may favor the forward reaction. But if circumstances change, circumstance B may favor the reverse reaction. Guess what? We have to be adaptable, right? Because we don't know as an organism which one we're going to get. We're living out there in a very unpredictable world, a very chaotic environment. And so we have to be able to go back and forth because we have to be able to respond to each circumstance as they change. Okay, so I saw Melissa first and then Christopher. Go ahead. Do what? Yes, I mean, the whole idea of that's a more of a much more extravagant example of the reversibility. So going through a feedback, letting a feedback loop and back to normal homeostasis. So that would be an example of the forward and reverse, but like in a very like upper kind of a broad view of it. Well, don't think of it that way. So it's not really a hypothesis. So when we're taking a look at like a situation like this, think of it more as your ability to sort of bob and weave with the environment, right? Because like if I'm in a fight, then I don't know where the punches are coming from, right? So depending on what's coming at me, I need to be able to duck to the right. But if the punches are coming from the right, then I want to be able to duck to the left, right? If I can't do both back and forth reversibly, and I can only go one direction, then half of the time when I'm moving to the right, I'm going to be moving into a right hook and I'm going to be flat on the ground, right? So having the reversibility, the ability to duck to the right or to the left, depending on where the punches are coming from, gives me the adaptability to survive. I can guarantee you, if all I could do was to the right, I'm going to be kissing tarmac, right? But if I'm going back and forth, I've got a fair shot at avoiding those nasty hooks. And that's what the environment's doing to us. This is the reason why biology is not interested in completion. We need to be able to bob and weave back and forth because we never know what circumstance we're going to be in. And we have to have that adaptability. One of the big patterns in biology, and I always say this all the time, is whatever is done must be undone. Oh, it doesn't stop there. And then redone. And then undone. And then redone. And then undone. And then redone. And then undone. And then done and undone and done and undone and done and undone. Think of it this way. How many times do you think somebody's flipped that light switch? Can I switch it again now? Yeah. Will I be able to switch it again tomorrow? Right? Why? Because we designed it to toggle reversibly back and forth. One set of circumstances favors the off position. Circumstances change, favors on position. What's going to happen? Circumstances are going to change again, aren't they? Off. And they're going to change again, on. And they're going to change again, off. And for as long as circumstances continue to change, we will be able to do and undo this response. Same thing is true in biology, only on a global scale. So Crystal first, and then Christopher. I mean, well, almost none of them are actually. I mean, some of them are close to completion. Like when you're making stuff like a neuron, you're not going to come back from that one, right? So there's some points of no return on that one. And there's some reactions, say for instance, where like you have A plus B and like the forward reaction is very strong and the reverse reaction is very weak. So they're, that's kind of tilted toward one direction or another. And there are some like that, but is it possible to go backwards? Sure. Right. I mean, and then with biology as well, like for instance, in this A, B, C, D one, another thing that could maybe make this look more like a complete forward reaction is if we don't need this because we eat this, right? So if we get A and B and we can consume that in our diet, then we don't need this one, right? Even if we have it, we don't use it because we have this in our diet, right? So that's another way to kind of change these. So Christopher, I saw it, and then Melissa. It doesn't matter. Everything. So when you're talking about chemical reactions, it covers anything that's in a chemical reaction. Well, no, you can stop it, actually. We actually have quite a few toxins that do quite a good job of stopping it. So, yeah, I mean, there are ways you can stop it because the basic mechanism of how to generate an action potential, which literally is just a wave of sodium ions, that's basically what it is. That's how you get that charge thing going on. You can stunt that wave. So you can stop it. It's not like a tsunami where you have no hope against it. It's like you have to continue to propagate that. It's like a rolling mechanism. So if you stop that mechanism, like if you don't continue that wave, it's like a wave at a stadium actually, right? So you kind of get it going and this section stands up and then this section stands up. Well, guess what? If you guys don't stand up, it's over, right? So you can do that with action potential if you want. Now you don't, but just because you don't doesn't necessarily mean you can't, right? Because there are some situations where you may need that. You just kind of keep that on your shelf. Is like, you know what? Probably not going to need this, but I got it in case I do, because you never know. Yeah, well, if they're tachycardic, probably what they're doing is they're giving them some probably like acetylcholine or something like that, something to just reduce. That's kind of an inhibitor of the original pacemaker cells to kind of slow down the rate is probably what they're doing there, which is kind of cool because you can actually do that on like real hearts and see the heart rate slow down. It's actually pretty cool, like not like a real person, but like a frog. There's a lot of cool stuff like that. But So I will see you in A&P. Yeah. Yeah. So, so now what's next? Water, right? So let's go ahead and take a look at water. We got a couple of minutes here. And what I want to do is kind of get us set up and started on this one. The first thing I want to do is, first of all, take a look at the structure of water. Because ultimately, all the properties of water are essentially driven by hydrogen bonds, right? And so we took a look at hydrogen bonds. And what I want to do is I want to take a look at hydrogen bonds with respect to the structure of water. We know water is polar. We know it's composed and capable of making hydrogen bonds because of the hydrogen and the oxygen. But now what does it actually look like? And this is what I want to do. So I want to, this by the way is a typo. When you see this, it's not true. The oxygen is not partially positive, it's partially negative. The hydrogen is the one that's partially positive. But here's what I want to do. What I want to do is take a look at the structure of water before we get to cohesion. So this is where our properties start, but I want to kind of sketch out a little bit what water actually looks like. First of all, structurally, shape-wise, and then the way it actually looks in concert, like in a lake or something like that. So obviously we have our Bohr model here. So we kind of saw this one already. But when you kind of have this sort of agreement or this sort of hybrid orbital between hydrogens and oxygens, and you sort of reorganize and reshape your electron cloud, typically what happens is you kind of create a very standard shape called a tetrahedron. And so typically what happens is when you take your 4 bonding spots, right? So of your 8, your 2, 4, 6, 8 slots for your 8 electrons, what happens is if you take a look at water, then 3 of these guys shape-wise actually look like they form like a little bit of a pyramid shape coming off of the oxygen itself. Now that's kind of like, it looks like this, right? And then coming up above it is like a little stick where another bond can form. And a lot of times students will ask me, well, wait a minute, when you draw water, how come you draw bent like that? How come not straight? And the answer is because that's its actual shape. Oxygen has an angle of 104.5, which is not something you need to remember, but it's not 180 degrees, right? So it's bent in nature. Well, the question is, why is it bent? Well, it's bent because when you form the shape from this rearrangement of the electron cloud, when you add all these molecules in there, those 4 places like 2, 4, 6, 8, when you sort of form the shape, they all have basically a common shape that looks like this, the tetrahedron. Well, now let's take a look and see then what we have in these 4 slots. In 2 of these slots, what do we have? A lone pair of electrons, right? This one here and this one here. Those are the ones that are happy, right? So here and here. So those aren't bonded to anything. They don't need to be, right? But what about the others? Well, the other 2 are bonded to hydrogens. So this one's bound to hydrogen and this one's bound to hydrogen. So if you were to take a look at this, then what you would see is not the long stick, right? But you would see essentially 2 lone pairs attached to a bent molecule, because that's what's left over. So really, oxygen looks like this, or water looks like that, where the oxygen is slightly negative and the hydrogens are slightly positive. Make sense? And that's the reason why it's a bent molecule, why it's always written bent. Now, what I want to do is draw kind of a picture of what these polar molecules look like when they're in concert, when they start to form hydrogen bonds with each other. In water, like this nice little placid lake right here, what you have basically is water molecules, which have these positive-ish hydrogen tails. And when they see a fellow water molecule like the oxygen, they form a hydrogen bond, right? So that's what this guy is right here. But guess what? There's other water molecules around here. And they basically just keep on forming these associations with each other. And so forth. So you can see what you start to form is this kind of fishnet-like structure that kind of forms like this chain link fence of water molecules in the water. So when you take a look at water, basically that is these individual water molecules all zippered together with each other, like with hydrogen bonds. Okay. If you want to use kind of an analogy for us, then it would be kind of like we would like if we're all individual water molecules. And then what we did was basically grab hands, like join hands all across the room. Like I would have two people, so I'd grab onto the right, so like this. So I'd have two, everybody else would have two. We all kind of interlink across. That's what water molecules are. Right? They're all kind of joined together. And that forms one of the first, and the cohesion thing, when you're talking about the diver, remember it across, you have to remember it across a weekend, unfortunately, but that's where we're going to define these first three. Okay. And then we'll talk a little bit about how water behaves relative to these traits and what biological impact that gives us. So we'll start that hearty discussion and really valuable discussion next time. The common syllabus one or the quiz one? That, yes. Yeah. And if you're wondering, there is a common syllabus quiz. It was originally due the 27th. I kicked it out to the 3rd. It's there just for the department to check to make sure that everybody is consuming the syllabus and you're kind of getting the nuts and bolts of it and all that sort of stuff. So it's in the quiz section, the quiz tab. Do it. I haven't figured out what to do with it just yet. Just do it, just so that the department can see that you did it and you got some sort of activity on it. And then I'll kind of make the numbers and stuff like